Now, when I come to discuss chapter 3 is what? Yes, chapter 3 is forces. To understand forces, we need to understand Newton's laws. How many laws of motion do we have? We have 3. And the first 2 are the important ones. Newton's first law states that an object at rest remains at rest. An object in motion remains in motion unless acted upon by a resultant force. So if the forces acting are balanced, equal and opposite, this means no resultant force. And this means your object is either staying at rest or moving with constant velocity. That's Newton's first law. Newton's second law is completing this and saying that, what if the forces are not balanced? What if one is bigger than the other? Then the object is going to accelerate in the direction of the bigger force. It's going to accelerate in the direction of the resultant force. And here we had an equation of Newton's second law, which states that F equal ma. F equal ma. And F here represents the resultant force. If for the same force, the mass is more, then the acceleration would be less. If for the same mass, the force is more, then the acceleration would be more. So we can understand that the acceleration and the force are directly proportional for the same acceleration, and force are directly proportional for the same mass, and mass and acceleration are inversely proportional for the same force. So using the same force, if an object is more massive, it would have less acceleration, and vice versa. This is Newton's second law. Newton's third law, you just need to know the statement, which is for every action, there is a reaction equal in magnitude and opposite in direction. And it's clear, very clear, that a force, whenever applied to an object, can change almost everything except the mass. Can change the shape of an object, the size of the object, can change the speed, speeding up, slowing down, changing direction. All these factors can be changed using a force, except, exactly, mass cannot be changed. Always remember this. When you come to determine the net force, if the forces are in the same direction, you add them. Forces in opposite directions, you subtract. Perpendicular forces, you can use Pythagoras theorem to find the resultant, or you can use triangle method in drawing or parallelogram method in drawing. What about, guys, friction? Friction is very important to understand. Of the very famous examples of friction, air resistance or drag. Let's imagine an object falling through air. What's going to happen? 3 stages. Do you remember this? At the beginning, it falls with constant acceleration, which is gravitational acceleration, g. And as the speed increases, air resistance increases, acceleration decreases. So at the beginning, it was constant acceleration due to gravity. Then as the speed increases, air resistance increases, acceleration decreases, until the forces are balanced. When the forces are balanced, it reaches to 0 acceleration or constant velocity that we call it terminal velocity. What forces are we discussing here? When an object is falling through air, there are 2 forces affecting it, the weight acting down and the air resistance acting up. So at the beginning, constant acceleration, then decreasing acceleration, then 0 acceleration when the 2 forces balance each other. At that stage, it reaches terminal velocity, which is a constant velocity. This part is really very important. Next part, Hooke's law. Now, what about Hooke's law? Hooke's law is applied to springs or to metal wires, not to rubber bands. And what does it state? It states that an extension is proportional to the force applied in a spring up to the limit of proportionality, exactly. And the law itself, F equal Kx, where K is the spring constant, and the spring constant can be found from the gradient of Fx graph. And at the same time, we need to remember that the spring constant represents the stiffness of the spring. So the greater the spring constant, the stiffer the spring is. You understand that K is measured in newtons per units of length. It can be Newton per meter, can be Newton per millimeter, or it can sometimes be Newton per centimeter, depending on the givens in the question. Remember F equal Kx, that's Hooke's law. If they asked you state Hooke's law, you can write the equation F equal Kx, and you need to say what is F, what's K, and what's X. Or you can write that X, the extension, is directly proportional to the force applied up to the limit of proportionality. And remember that when a spring exceeds the limit of proportionality, first, it doesn't go back to the same size, it doesn't go back to the same length. Why? Because it went from the elastic region, which is before the limit, to the plastic region, which is after the limit. So after exceeding the limit of proportionality, the spring is permanently deformed. It cannot go back to the same original length as before. And same after exceeding the limit of proportionality, using the same force as before, it extends longer distances. So you can understand that after exceeding the limit of proportionality, the stiffness of the spring actually decreases. And this results in more extensions for the same amount of force. Even using less force than before, it will have more extension than before. Last part, circular motion. And this is the last part in chapter 3, and it represents any object moving in a circle, like a car moving around a circular orbit, a circular track, or let's say a bucket of water spun with a rope, or a moon orbiting Earth. In all cases, we have a force called centripetal force that is pulling that object towards the center of the rotation. This centripetal force is affected by the mass, the speed, and the radius. The more massive the object is, or the faster the object is, it needs more centripetal force to keep it in the circular track. But if the radius increases, if it's moving in a bigger circle, it needs less force.